Hi everyone, my name is Olivia. I'm presenting today from Lexington, Massachusetts, and I want to thank my mentor, Sydney Plummer, for helping me complete this project and supporting me throughout the process. So my project's title is Coping with Climate Change, Evaluating the Plastic Responses of Brittle Stars to Ocean Acidification and Ocean Warming. So to talk a little bit about why I chose to study ocean acidification and ocean warming, ocean acidification, um, often abbreviated as OA, occurs when atmospheric carbon dioxide is absorbed by seawater, and ocean warming is linked with global warming, and it is just the rise of ocean temperatures. So I thought ocean acidification and warming were very important topics and processes to study, and especially their combined effect because both of them negatively affect marine environments, and also that impact carries on into communities that rely on marine resources. So the chemical process of ocean acidification, I created this diagram here to explain a little bit about it. So it begins with the absorption of CO2 into seawater and reacts with water to to form carbonic acid. And this carbonic acid then dissociates into bicarbonate ions and hydrogen ions. And the hydrogen ions circled in red here are what drives the decreasing pH and the acidifying of the water. So at the bottom here, I have some calcifiers pictured, which are organisms that use calcium carbonate to create their shell skeletons. And they are known for being one of the most heavily impacted groups of organisms by acidification because they use calcium ions and carbonate ions to create calcium carbonate, and carbonate ions react with hydrogen ions to form bicarbonate ions, which is shown in step 4, and thus there is a underavailability of carbonate ions for calcifiers to use. So why did I choose to research brittle stars? Well, brittle stars are very ecologically important. Burrowing brittle stars contribute to bioturbation, which is the moving around of sediment particles on the seafloor, and biogeochemical cycling. An example of this would be oxygen flow on the ocean floor. Research also suggests that echinoderms, which are a group of marine organisms that includes brittle stars, are more resistant to OA than other groups of organisms. And in general, there was a lack of research that I found on brittle stars. So to evaluate the responses of organisms to ocean acidification and warming, I came up with the question, how do brittle stars plastically respond to OA and OW? So to explore this, I would need to identify traits that facilitate these plastic responses or acclimation responses. I also assess the vulnerability of different globally distributed species to OA and OW, and I began with a literature analysis of research papers published in 2013 until now. So I first compiled a table of key findings from different studies. They evaluated the neutral, positive, and negative impacts of OA and OW on brittle stars through quantifiers such as survival, growth, metabolism, and calcification. So survival was generally negatively impacted. Growth was also generally negatively impacted. Calcification was neutrally impacted, and metabolism was positively impacted. And this is for ocean acidification. Um, in terms of ocean warming, survival was negatively impacted. Calcification was also negatively impacted. Growth was neutrally or positively impacted, and metabolism was positively impacted. So I'll talk about the physiological responses and the behavioral responses that were researched. So the first physiological response was upregulated metabolism. of brittle stars. So the undersaturation or the underavailability of carbonate ions available to brittle stars um, resulted in them increasing their metabolic rate in order to keep maintaining their calcium carbonate structures. So on the graph to the right, um, it depicts oxygen uptake rates in acidified and warmed waters. And oxygen uptake was used to measure the metabolism of brittle stars. As you can see, oxygen uptake increased as pH decreased and also as temperature increased. There was also an increased net calcification rate observed in the brittle stars. So low pH or acidified water causes calcium carbonate to dissolve, and thus brittle star-driven calcification increased in order to help them compensate for dissolution. So some of the behavioral responses that were observed were slower response time. Scientists measured response time using the writing response, which is how the brittle stars returned to their normal position after they were flipped over. And there was an increased writing time overall, so slower response time, and a potential biological cost of this could be vulnerability to predators, as the brittle stars are less able to escape and move quickly. Arm retraction was also observed in burrowing brittle stars. On the right is an image of a burrowing brittle star, and as you can see, their arms are sticking out of the burrow. And so brittle stars exposed to acidified water retracted their arms into their burrows. And this was an important finding because brittle stars use their arms for suspension feeding and ventilating their burrows, so potential cost of this behavior could be limited food access and reduced ventilation of burrows. And the goal of these behavioral responses was so that the brittle stars could conserve energy and reduce movement. So there were also some energetic costs um, that I found when I was evaluating the sustainability of physiological responses. Muscle wastage was observed because of an energy deficit caused by the increased metabolism, and this was manifested in loss of muscle mass in the brittle stars. Acidosis also induced decreased metabolism in certain cases. Acidosis occurs when there's an there's an excess of acid in the body of the organism, and this was found to be caused by longer-term exposure to more severe levels of acidification, and brittle stars were unable to regulate the acid-base changes. So my vulnerability assessment included creating this map of globally distributed brittle star species, and I have 9 species that were found across the world that were included in the studies that I analyzed. So intertidal zones, brittle stars that live in um, intertidal zones were found to be more resistant to ocean acidification and warming in general because they are naturally exposed to variability in pH and temperature in their natural habitats. Whereas polar regions, brittle stars that lived in the Arctic or the Antarctic, experienced a narrow thermal tolerance range and uh, were generally more vulnerable, more heavily impacted by ocean acidification and warming. And these regions, our polar regions, are also predicted to be more heavily impacted by future acidification. So to summarize the main points of my paper, the combined impact of OA and OW is essential to research because they have complex interactions and there's a lack of research currently on their combined impact. The plastic responses that I found were metabolic upregulation, increased calcification, arm retraction, and slower response time. However, the response sustainability showed that there was a risk of acidosis in the brittle stars and muscle wastage as well, which was caused by an energy deficit. In the vulnerability assessment, I concluded that intertidal areas were better suited to acclimate to future ocean conditions, and polar regions were more vulnerable to OA and OW. Thank you for listening.
Thank you, Olivia. That was fantastic. So we do have some questions for you. The first question is, did you encounter any conflicting information in your research? And if so, how did you evaluate which sources to trust?
Yeah, so I definitely did. As I mentioned before, the complex interaction of OA and OW is very difficult to quantify and very difficult to study. So in my table, which I didn't have on the slides, but it's an expanded version of the data from both of the graphs, and it also included combined impacts. I included each separate finding from a study, which um, I found it was difficult to summarize the findings for combined impact. So I included that as one of the research limitations in potential future directions.
Oh,
Yeah.
yeah, great. Thank you. And the last question is, if you could continue this research, what would your next step, what would be your next step or follow-up questions?
Yeah, so there are a lot of potential future research directions. Um, I think it would be very interesting to study the adaptation potential of marine organisms to climate change because in my research, I only studied the acclimation potential. And I would also say that longer, I would want to research studies that had longer exposure periods because longer exposure has shown to have different effects compared to short-term experiments. And I would also be interested to explore how other environmental and biological stressors affect brittle stars in their natural habitats, for example, food availability or displacement of individuals between different populations, because most of the studies that I did analyze were conducted in the laboratory and the scientists manipulated different factors.
Thank you, Olivia. Great work today. Thanks for presenting.